Thanks, Bill. Thanks, Lyron and Tom, for setting up the desk for virtualization and cloud platforms. We have seen yesterday about MPI, and we have shifted gears to the cloud and virtualization technology. So I'm going to talk about two topics of it. One is how some of the infrastructure is being built within the adapter for virtualization, and second one is about handling the dynamic workloads. So the first one, there are various kind of virtualizations that we have seen. The most easy one to do in from the hardware point of view is an SRIOV, where you have multiple VFs and PFs, each with its own different view of resource and the entity of the whole notion of a device, which is easier in that aspect. The second one is mapped physical devices to the guest as a multi-channel, so which is still close to an SRIOV, but it's only PF. There are multiple channels for the same physical port as the devices. So there will be 16 to 8 physical functions as PF sharing the same physical port as multi-channel devices, and these are mapped to every VM, every different VM, because they want high performance, but they are unlikely to use the SRIOV for the QoS and their own legacy deployments. Third one is what we have seen is para-virtualized devices, where the performance really does not matter, but you want the scalability and the access from every different VM with the own set of QoS and policing and the filtering parameters that you want. And the fourth one is a software-based virtual device, which is a pure device emulated in user space, and QEMU or KVM kind of OS uses those devices to expose to each guest VM. And the fifth one that I'm going to talk a little bit in my later part of the presentation is virtual devices which are mapped to a physical device, which runs as the same performance level as what any SRIOV or any PF device operates at. So this is a very high-level view of how the virtual devices look like. What I just spoke about is at the right side in the adapter 2, you have a multi-channel adapter where you have one PF and there are small shadow PFs similar to the PF, and each of them are mapped to the guest VM. Then you have the SRIOV devices with PF and VF, where the resources are distributed among PFs and VFs. Each is mapped to a different guest OS. Multiple devices could be mapped to the same guest OS, and you can set the same QoS parameters what Lyron talked about in the previous presentation. Para-virtualized devices, as you see, is not there in the adapter, but they sit in the hypervisor, and they are mapped to the guest VM. But you can see that they are talking to the PF for some reason, and there are specific properties that every para-virtualized device has it, and that's something that PF provides to it. So I'll walk you through them. So every para-virtualized or virtual device that we create on an Ethernet or a NIC RoCE side has got two main properties. One is a MAC address, and a VLAN has got a bunch of other small parameters or properties such as multicast, promiscuous, disparate mode, VLAN promiscuous, multicast promiscuous. Keeping those advanced parameters aside, what we get at a basic level on every interface is these two properties. There can be one or more such interfaces that you can create for a given PF, and each of them can be mapped to a guest VM as a para-virtualized device with those properties. And when you have that, you are still mapping to multiple host CPUs, and when you want to access those devices through multiple CPUs for the NIC performance, then you still have those RSS queues. So a NIC device which has NIC properties of multiple RSS queues, and then you have got RoCE queues, both of them are handled by the same device. And there are various different operating systems that make use of this various filters are at a different level, which are bound to this interface object called NIC interface here, which is a property of MAC and VLAN. And as the traffic workload changes on those VFs or those NIC interfaces, many of the operating systems tend to move the filters along, and that brings the complexity on the RoCE side. And to avoid those complexity, what we do is define a virtual interface called NIC plus VLAN pair as an interface, which is a driver level OS construct, which uniquely identifies RDMA virtual device and a NIC virtual device. Many OSs call interface or a vPort or other terms to represent this NIC interface object. When we do that, what we see here is we have a physical function has multiple NIC interfaces, and what our adapter can do is create one virtual or physical RoCE device, RoCE plus NIC device. When we say RoCE, NIC is always out there on as a support functionality, and every such device can have its own GSI QP1 to establish the connection. And there is one connection management which obviously will take care of each of the GSI Q pairs. This poses a need to scale how many number of Q pairs, GSI Q pairs we can have in an adapter. And we look for a better solution that can we have one GSI Q pair shared among multiple of those devices as we move on. So that's the second mode in which we would like to have one GSI Q pair shared among multiple RoCE devices. And instead of creating multiple RoCE devices, why can't we have just single RoCE device? But there could be multiple NIC devices. Each is having a different vPort. And this model scales well with from the adapter point of view, where you don't need to create multiple Q pairs. And it's the OS choice to make which model that they want to go forward with a shared GSI Q pair or multiple GSI Q pairs bound to each device. And it can be configured in either of the way. We believe that this is probably the way to go forward, to have single device and single GSI Q pair. I wanted to talk about some of the RoCE v2 aspects here. I'll touch upon that. However, I see a large interest here in RoCE v2. It's probably 3 o'clock is probably a good time if we have cycles to, some of us can walk through the RoCE v2 changes as a whiteboard session or something that might satisfy our needs. Coming back to here, so RoCE v2, for all these virtual devices, any GSI Q pair 1 can accept RoCE v1 or RoCE v2 packets, and the adapter discovers, finds out, does the packet parsing, which type of packet it is, and it tells to the OS, so that the OS does not need to parse the whole packet again to find out whether it's v1 or v2 while it's establishing the connection. Those are some of the fields that comes through a CQE. In order to support connection management at a much faster rate, some of the commands that we do traditionally in RDMA to move from reset to init to RTR to RTS could be accelerated, and that's one of the features that we support is transition the Q pair right from the create state to the RTS state. I remember some of last year, somebody from the MPI community asked for avoiding multiple stage transitions, and this is one of the feature. It's not out there into open source yet or into an IBTS spec, but that's something that we would like to try there to avoid multiple state transitions wherever the client or server wishes to do so. The other important aspect of this is when we have these virtual devices and each of these virtual device mapped to a different NIC adapter, NIC virtual port. These Q pairs can be created and destroyed. While it is done, it's the modify Q pair state which allows us to bind to a specific V port and filter the packets for that V port for that Q pair, rather than binding the Q pairs at a creation time. So the stack could take a benefit of creating the Q pair once, but keep recycling it for one or multiple virtual functions or VFs of the NIC virtual ports which are mapped to a different guest VM by modifying those QP states when during the connection establishment stage. Since we moved on and have this basic understanding of NIC virtual ports, shared GSI Q pair, and single RoCE device, I'd like to walk through some of the Linux vRDMA prototype work which is in progress right now. Is a primary support for extending the RDMA devices for the Linux containers, which is a buzzword, and it's getting a lot of attraction right now to get it deployed in the cloud engines and cloud deployments. So what we have is there is one physical function or a PF, no SRIOV. There could be one to multiple NIC interfaces, which translates to a different netdev into a Linux kernel. And for each of such netdev, we can have one virtual RoCE device being created. And each of that virtual device can run at the same performance level as the physical device, because it's just mapped to a physical PCI function, but it's just a virtual construct in the OS. And each of that virtual device, if you see here, is mapped to a different Linux container object when they have been created. So those virtual devices allows us to have the resource partitioning for all the kernel consumers that we operate with, which is ISR or NFS RDMA or SRP. So when they work, they get a very restricted view of the resources that they see, which otherwise, if we don't do it, could be can see all of which is available and can make wrong decisions of how much resource to use, which we'll see in our next presentation. The second aspect of the vRDMA device, which is orthogonal to, is the C groups. We have been knowing the C groups for long now for block devices, for CPUs, for memory, and the device C group is primarily extended here to limit the RDMA resources. So C groups and virtual device, they both are orthogonal, and the C groups primarily applies to the user space processes which have been created to make use of those. So whenever the processes are created or destroyed, they belong to a particular C group. And when they query a device, they get to see only amount of resource that's been given to them. That applies to PD, all RDMA resources that we can think of right now, PD, CQ, SRQ, QPair, address handles, flows, memory regions. All of those is controlled by a device C group. I would like to hear if we have an opinion to have a different C group for RDMA or to have just an extension of a device C group. We believe that RDMA device is just an extension of regular devices, and it belongs to a device C group unless it brings a different set of complexity. Coming to the APIs, we have a very simple set of APIs for now. How does these virtual devices for the containers are created is a simple set of verbs to create a virtual device where we say, this is my physical device, create one virtual device for me, bound to this netdev. So at a given time, virtual device is bound to only one netdev. And so you can destroy those. there are always unique name for every virtual IB device that we create. So obviously, when we create two virtual devices with the same name, it's going to fail, even if they are in a different namespace within the containers or within the network namespace area. Which could be further extended if we see that the same name is a beautiful feature to have between two container objects. At presently, they are not unique names between two container objects. Configuration, we have provision APIs. So this provision APIs is for every virtual device. You say I want this many PDs, MR, Q pairs for this virtual device, and then it could be an oversubscription provision model, or it could be one-to-one. It's all administrator's choice to allow that. We believe that it should be one-to-one map and not an over provision, because most of the ULPs today that we have written are not capable of handling or running the traffic when the resource creation fails, and that's something that we need to address going forward to let it run even if it does not have sufficient amount of resource. So that's the provisioning part. And the other simple APIs that we have is there are hooks provided to the vendor drivers to register a virtual device and unregister a virtual device. So any vendor specific thing that we want to do is invoked through those APIs. So those should be called from the callback APIs when the virtual device is created or destroyed. Before they are unregistered with the OS, the vendor driver knows about it, saying these are getting destroyed or created. Let me finish my cleanup to perform any operations in that area. It could be QoS parameters, or it could be any internal provisioning that he has done, including interrupt moderation or number of EQs that it might have provision for this virtual device. How do we get an isolation in Linux containers? It just works because all the isolation for the user space application is through an IB context. One IB context does not talk to the other one. They all belong to the same process context, and so we don't need any other software construct to isolate one contained application with the other contained application which are using them. In kernel space, the virtual device itself is isolating himself with any other device, and so it won't have a view of the other device, and that just works. Performance, it runs at the same level as what we see with the PF device, because it's mapped to the every PCI function. So virtual device, all the post send, post receive, post CQ, all the handling, creating the queue pair. There's a very thin layer for the control path that goes through the resource provisioning model to make sure that this virtual device can be created. This virtual device can use this resource or not. So if it is a user space application, it would fall through the C group, and the C group would control this resource can be created or not. And if it is a kernel space consumers, then it would just follow the provisioning model of the virtual device. And they both are orthogonal, so the containers can still use the virtual device even from the user space application. There's no bar to it. This allows us the flexibility that between PF and VF, when we don't deploy an SRIOV, we can dynamically provision the number of CPUs and the number of vectors for every VF and PF. So when the workload is moving in that area, probably the virtual RDMA devices without SRIOV could be an advantage. So that's all I have. All the other rest of the isolations are provided by the protection domain, and so even though we have one PF, multiple memory regions, multiple queue pairs belong to the same PF, they are still secured with a PD. One application won't be able to interact with the other PD. And so the user context as well. There are a lot of things ahead of us that we want to do, which is not there yet, is the QP1 extension. Right now, QP1, there is one-to-one queue pair for virtual device and physical device. And this is the piece that we are still need to extend to, so that you, at least in Linux, where one queue pair one can service the request from multiple virtual devices, and needs to have a construct to know that this is from which device it has came through, all the way into the stack up to RDMA CM. When we do that, we need to isolate the JITs, because some of the JITs are going to be a proxy JIT, which are for a physical device, but they are mapped to the virtual device. And so when they are mapped to virtual device, any connection establishments that goes through a physical device should not have visibility into those JIT entries. So some of the RoCE v2 patches already does moves the JIT management from the vendor driver to the kernel OS, and that would be one of the handy features that will come in place to isolate the JIT entries, where we will have special flags to indicate that this JIT does not really belong to this PF, but it from the OS perspective or RDMA CM, this does not belong to the PF, but for the physical device, it still belongs to a PF for him to establish the connection and accept the packets for those JITs. While doing this exercise of the virtual RDMA devices, one of the motivation was to do multipathing. Some of us spoke already about the multipathing with RDMA, and we see a huge complexity ahead of us in achieving the multipathing with virtualizing them. And we believe that it's probably the send read write operations is not the right place to trap or to achieve the virtualization. There has to be a more higher level words or higher level transactions to be defined, including making an memory registration probably as a memory advertisement as an IB spec, which is not there yet. And quite a lot of complexities in area of virtualization and multipathing arise because the memory registration on the wire is very ULP protocol dependent. So we see the virtual device is probably a platform to define these higher level verbs to which can send the traffic across multiple queue pairs, where the queue pairs and device is being detached up to some extent, and obviously the OFI is moving in that direction, which we believe that could translate some of the OFI words probably into this. The OFI interfaces could translate to this higher level transaction level verbs, and those could be applied to the virtual device. So that's all I have for virtualization support for the Linux containers. Any questions? Yeah.
Turn it on.
Okay, so 2 questions.
Sure.
The first is, when you say that you bind the virtual device to an interface, what do you consider an interface? Is that an interface of your virtual function, or an interface, any software interface that can be in Linux?
So in this case, the 3 boxes of RDMA NIC you see and the VLAN NIC interface is actually a netdev here.
There are netdevs of virtual functions, though?
No. So in this case, there are no virtual functions. This is one PF. There are multiple NIC interfaces being created, and each is mapping to one netdev. Okay. The Linux netdev. And so if you don't enable the virtualization, then you would have the JIT table consist of all the entries from all the VLAN dev or any of the bonding devices. And when we create the virtual device, we detach that netdev from the primary netdev, and it just gets attached to this new RDMA device. So in that process, the JIT would get removed from the physical, the primary PF or the primary RDMA device.
Okay, so why do I need a new virtual device to do that? I mean, RoCE already has a multi-entry Git table, which is meant to hold interfaces. So each Git entry represents whatever interface Linux has, whether it's virtual or 10 virtual bridges on top of that.
So I see your point. We see the vrdma device as a vehicle to support multiple functionalities. One of them is that a year later, when we have the containers doing their own mounts from an untrusted Linux container doing the mount operation for NFS RDMA, he needs to have view of only those many MRs which are given to him, and not do it the endless mounts taking over all the resources, where some of these memory regions and queue pairs could be created within the kernel outside of the process context. And doing the resource provisioning at a device level by creating the virtual RDMA device is probably one of the way to do it.
Okay, so this is one way. The other way might be just not to expose the IP addresses that container is not supposed to see, or expose but prevent it from referencing them as an index in QPs or address handles. Again, I don't see here the need of creating a new abstraction of a virtual device. You can achieve the same behavior with the existing model.
We can still achieve it, but we can't control it for the kernel space consumers. For user space, as we reviewed, the cgroup just works for all the user space applications that we want to create.
Okay, thanks.
Yes, please.
Don't you need a separate UAR page for each container, though? You do need some separation.
That's right.
With the device. And that's what I assume was the reason you were creating, one of the reasons you were creating.
So the IBV context, when you create a U context, it translates to one of the UAR page, and that's where we'll be able to get the isolation between those two. So we might want to restrict how many U context. So I missed that U context is also one of the covered into the C groups, and U context is the primary object where all the objects are linked. And so when we create the C groups and we create the processes, they're all bound to the U context, and all the resource monitoring is done through the U context. Yes, please.
Shared GS or QP model. It seems that there are security implications. I mean, you're going to need to put it on a global VLAN ID, which means that the peers will need access to that VLAN ID, which means they can attack each other as well as the CM. How's that protected?
So there is two levels of filter. One in the shared GSI QP model in this particular for a specific OS. Whenever the GSI QP is created, they are bound to only those NIC interfaces. It can accept packets only from those NIC interfaces which belongs to this PF or VF. Meaning, if I get a GSI packet which does not belong to this VLAN, the adapter is going to drop it. So the interfaces could be created much later after the GSI QP is created. When the
I'm concerned about the end-to-end nature of the connection manager.
Uh-huh.
Are you putting the same connection manager on each end of the connection? What if it's a third party or not your connection manager? How do you guarantee that security level?
So in some of the OS, the connection manager is within the driver.
Well, right, but that's the problem. How do you trust that remote OS? It seems to me that it could be a guess, which is to say untrusted.
So for untrusted guest, the vports are created by the hypervisor. And the hypervisor knows the MAC and VLAN.
So they'll be injected into that vport, which will therefore be tagged with that vport's VLAN.
That's right.
And anybody can recognize it to reject it. Okay.
Yeah. So when the VMs are created, when the vports are created later on, after the QP1 is created, then the adapter insert into its filter list saying this particular interface, this VM is enabled for an RDMA service, and so therefore I need to insert MAC and VLAN for this VM. For the other VMs, which still does have a NIC interface, but they are not enabled for RDMA, and therefore I would like to skip accepting QP1 packets for all of them.
Okay, you have to think that through with some rigor. It's
Okay.
good.